Today we have with us Beata Turoňová. She is group leader at Max Planck Institute of Biophysics, and her group aims to facilitate in situ structural analysis by developing novel algorithms for cryo-electron tomography and subtomogram averaging. Beata is going to present us novaCTF, a widespread algorithm for estimating the CTF and reconstruction tomogram.
As mentioned, I will be talking about novaCTF, which allows for 3D CTF correction for tomography. I'm currently project leader at the MPI of Biophysics in Frankfurt, and this work was done already 4 years back, actually, when I was still as a postdoc with John Briggs. So before I start on novaCTF, there is maybe a bit more about the contrast transfer function in general. I assume you all know it. It's a bad guy in the field because it always complicates things. So what it does actually, it modulates our signal when we collect our data at on the microscope. So if you would have, for instance, a gold bead in our sample or some spherical particle, and we would collect the data and reconstruct it, it ideally would be a sphere, but in tomography we have different issues like a missing wedge that elongates the things a bit. So still we would get something like that if we reconstruct a signal that would not be modulated. However, because of the CTF, we have a spread of the signal, and instead of getting this nice, at least in one dimension spherical bead, we would get something like this. It basically reminds one of stone being thrown to the water, and it gets this nice, or not nice, but it gets this circles around it. So it's not so apparent when you look at your data, because typically what also we have in the tomographic data is a lot of noise. So it's never so visible like that, but nevertheless, that's exactly what's going on. So if you collect your data, the signal is always somehow distorted in the similar way. And if you would go more to the mathematical side of this, it's basically the contrast transfer function can be described as a sum of a sine and cosine wave, and the most crucial part is that it's dependent on the defocus. So there is the parameter that influences how bad or how good your contrast transfer function is. So if you would actually acquire our data in focus, so if you could place our sample in focus, ideally, if it will be really thin, then there will be no modulation. So if this will be what we will get 100% of our signal in the way we would expect it. This is never true. Even if we are in focus, there is still some modulation, but in ideal case it would look like that. However, in cryo settings, we never acquire in focus. We always have a bit of a defocus, and our signal becomes modulated somehow like that, which actually corresponds to these nice waves we saw in the image before. And what it actually means from the practical point of view is, if this is the resolution, we know that this is the signal we can rely on until it first crosses the zero, and then it basically has inverted contrast. So what we could actually realistically get of our tomograms without any CTF correction would be a resolution up to here, I don't know, 16, 17 angstroms, and all that comes afterwards is not reliable as long as we do not correct for it. So we have to somehow do something about this. And to show you, because I said that it's actually depending on the defocus, it's to show you a bit of this effect. If we are the closer to focus we are, the more resolution we can recover without any correction, but also we get a worse signal. So this is the virus. This is actually HIV, but you can barely see it. And if you go more out of focus, then you see that the virus becomes nicer in the sense that we have a better contrast. We can actually see the virus. However, we also see that the function moves, and we lost the resolution that we can recover, because now it's not 16, but it's 25 or something like this. And this modulation, it can be nicely visualized when we go to Fourier spectra. This is the corresponding one to those images. And you can see here that these waves are really a bit more spread here, while they are more tight here, and they are also getting more noisy. And you can also see here that once you reach to the really high resolution parts, that should be somewhere here, then we can no longer even fit the function reliably because there are no rings, although the function would actually be behaving like that. So what we can do about this now is we have to somehow correct it. So at least we have to try to get the contrast on the same side. So do something we call phase flip, where we actually make sure that at least the features has the same, they have the same contrast when have the same contrast. And we can also do multiplication, which would also somehow boost the signal here and may try to push it up to this one. What we will never be able to do is to recover the signal loss at the zero crossings. These points are lost forever. But luckily, when we have more tomograms collected at different defoci, we see that the zero crossings are at different places, and we can combine those data to actually somehow compensate for the fact that we lose the signal here. So this all is true also for single particle projects, and this is something that's just going on in there. And even in single particle, we have to correct. However, tomography actually poses us, in many cases, a bit more of a problem, and that's because we tilt. So if we imagine this is our super thin sample, something like a single particle one, and we collect our first image in at 0 degrees, we see that most of the things in that very thin sample would have the same defoci value D. However, in tomography we tilt all the way up to 60, sometimes 70 degrees. And when we look at this 60 degrees still, we immediately see that this projection will not have the modulation caused by one defocus value here, but it will be influenced by the whole set of values going all the way from here to here. So it will suffer, it will basically have a defocus gradient due to the tilt. And this is already one problem. But what is actually even slightly worse in case of tomography is that we do not have infinitely thin samples. We do not have one layer of small proteins. We have, at least for proper tomographic samples, we have a bit larger thickness of our samples. So even in this case, even in the 0 degree, we can see that there will be objects in our samples that will have a different defoci value here and different here. And those, even the 0 degree image will be influenced by more than one defocus value. And now the question is how to deal with that, how to correct for it. So for a very long time, there was no CTF correction whatsoever because it was computationally too demanding, and also the tomograms or the tomography or subtomogram averaging were not reaching the resolution where people believed it matters actually. So they were not doing anything about this. And then finally came something called I2PC correction that dealt with this problem. So they try to compensate for this defocus gradient due to the tilt and still ignore the thickness. And this is something that is implemented, for instance, in ITOMO, and that's how it works more or less. The reconstruction on its own is very simple. So you collect your projection, you correct your projection with the so-called 2D strip-based CTF approach, meaning that at 0 till you assume only one defocus value, but here you assume this gradient, and based on the estimation, you basically split this projection into the stripes like that, and each stripe is corrected with a slightly different defoci value, producing this gradient. And then what happens in the reconstruction, it's very simple. So you have your tomogram, and for each voxel in the tomogram, you find out for each projection where it should land. So which pixel from this projection should correspond, and add it to this value of this voxel here. So basically, in this case, for the voxel V here, for instance, this would be added to this one, and you would do it for all the projections, and in the end you just divide by, actually you divide the sum by the number of projections that are contributing, and that's it. That's in a nutshell, as simple as that. There is some filtering going on, but this is not really anything that influences the CTF. And this actually already works pretty nicely. So if we go for a synthetic data example, we have a tomogram and we place a free. This example is in 2D, so it's disks, not spheres, but it doesn't really matter. We place one directly in the center, one a bit more high, but at the center in X, and one at the same height as the disk one, but more on the side. So here, the acquisition direction or the beam direction is actually from here to here. So even though it's square, it's a bit confusing. So now if we look at if we reconstruct, if we generate the synthetic data set and reconstruct it, as I said, we don't get the perfect disks back because there is the missing wedge problem. But this is the reference how it should look when there is no modulation. If we reconstruct, if we modulate with CTF and don't correct, we get something like this. We see that, especially the one that is far from the center in X, surprisingly, is very, very badly recovered. So imagine you would do the subtomogram averaging using those structures. You would not get such nice results, and the alignment would be really misplaced due to the distortions of the shape. And if we do this 2D CTF strip-based projection, we already see that the one that is in the center actually got reconstructed very well. But the more we go to the center, both in a Z and in a X, the more distortion we get. So actually, this shows that while this approach is good and good enough and definitely better than no correction, it's still not really optimal for samples, especially for the tomographic samples, especially if they are thick. Now, we then wanted to tackle the problem with the thickness and do something that is called 3D CTF correction. And when we started in 2017, there was already some groundwork laid by Jensen and Kornberg already from 2000. They tried to deal with the thickness of for the single particle projects with the thickness of the viruses actually. But they showed they approach only on the synthetic data back then because it was computationally too demanding. And a more recent one that came up at the same year was the one from Kunz and Achillas Fragakis. And they did something similar what we do, but they use a different reconstruction technique. It was the iterative one called SART. And they actually have a bit more complicated and computationally demanding reconstruction implementation because they actually were rotating the wall volume, which is not very efficient. And they showed some improvement of the structures, but the data set they chosen was not so high resolution. And also they compared not only 2D versus 3D CTF, but they also compared the weighted bed projection and SART reconstruction. So it was very hard to kind of dismantle the effects of this. So we took the work from Jensen and Kornberg and expanded it in a way that it would be possible to use it for a proper tomographic data set, meaning for large data sets. And what we did was actually, and that's actually what novaCTF is. It's also very simple. So when we think about our reconstruction space, we divide it in slabs. Defocus slabs. This is the only one additional parameter that has to be set by the user prior to reconstruction in comparison to the other reconstruction techniques. And what it does is that, for instance, here we decided that there will be the focus step of this size, and we will divide the reconstruction space in total 7 slabs. Then we take our projection, our tilt series, and we correct each of the image not once with one defocus value, but with, in this case, 7 different values. So we, instead of having 1 tilt series, we will have 7 tilt series in this case. And in each of these tilt series, there will be 7, the images will be corrected with a different defoci values. And then This correction, however, this 2D CTF correction is simple. It's not strip-based, so we really don't have any defocus gradient. So each image is corrected with only one value. But we have seven different values along the 7 different stacks. And then we do basically the same thing. So we have our tomogram. The only thing that we add is now that in addition to find the index in the image where we should take the value from, we also, based on the XZ coordinates, determine which of these 7 images we should use for the 0 tilt and which for the 60-degree tilt. So there will be just one more indexation necessary to actually reach the proper data. And as you can see here, for this voxel, we would know that this is the index we want from the 0 tilt. And we know that we should take it from the slab number 5. While here we know it should be slab number 6, which corresponds to this position here. And that's basically it. So that's the only difference. What I would like to point out here is that, as I said before, there is not only the Z height that is actually making the difference, because we can see that if we take these 2 voxels, they have the same Z height in the final tomogram. And they indeed, for the 0 tilt, come from the same projection and from the same slab. But once we tilt, then this one comes from the slab number 2, while the green one already is from the slab number 3. So actually there is the defocus value that one should use for correcting or for reconstructing the voxels is not dependent only on the Z height, but also on the X coordinate, which is something that is often not so apparent on the first glance. This is very efficient. The way why this is that we reconstruct or that we compute at the very beginning something we call the focus array. This is basically array that has XZ dimension and has as many images as there are images in the tilt series. And this is basically one indexation field, when then we can say, okay, this voxel has this and this is at X coordinate, and we should take for the 0 projection, we should take the value from the slab number 3, while for the 60 we should take the value from number 2. And here the same for the green, it would be same one for the 0 tilt degree, but a different one for the 60 degrees. So this is just one lookup table, so to speak, to fetch the correct index. And then we can simply just take the value from the already corrected image, which makes this implementation very efficient and time and not so time consuming. And if we now then compare how it actually looks like in comparison to the other methods, we see that with the 3D CTF, we can actually, regardless of the position of our beads, we can reconstruct them with the proper shape and with minimal distortions from the CTF. Now, having done that, we of course were more curious about how this will actually perform on the experimental data set. And back then, the data set with the highest resolution achieved was the one from my colleague Florian Schur of the immature HIV capsid lattice. So they had 43 tomograms in total, roughly 4K times 4K, with the thickness of 1,200 voxels, which means around 160 nanometers. It was a very large data set because it resulted in 130,000 subtomograms. The resolution, the original CTF estimation was done with CTF Find 4, and the original CTF correction was CTF phase flip. And the obtained resolution with the 2D CTF strip-based approach back then was 3.9 angstrom, and as I said back then, that was the highest subtomogram averaging resolution ever. So we decided to test our method on this one to see if we can actually improve the resolution or the structure. But first we had to establish this defocus step. So basically we have to decide what slab size we want to use and what makes sense. And for that we ran this simulation. We had this 130,000 subtomograms that we distributed within this 116 nanometers thickness and simulated 2D CTF correction, and we would find out that if the estimation would be precise, that would be this full line, and the dashed line would be with the estimation, the CTF estimation having some error of standard deviation 12 nanometers. We would find out that we have a resolution somewhere here, and that corresponds to roughly a signal transfer of 0.4, so 40% of the signal was necessary to go through to get to this resolution. And then we simulated it for the different slab thicknesses, and we ended up with, we tried 30 and we tried 15. This would be with the ideal estimation, but as I said, the more realistically it would be this. And we find out that if you want to have more than 50% of the signal transfer available at the Nyquist, it was 2.7, we should go with this 15 nanometer step. Going even lower, or better say going for like 10 or 5, would most likely not yield that much. So we settled on 15, which resulted in roughly 33 slabs, so 33 tilt series instead of 1 per 1 tomogram. Just to show you that this is actually a really thickness dependent problem. This is the same simulation performed on a thickness of 500 nanometers. So the slabs, they of course remain the same because they remain with the same thickness. But if the tomograms would be corrected with the 2D CTF approach and had a 500 nanometer thickness, we see that we would lose the signal already at the resolution of 8 to 9. So it's really the thicker you sample you have, then the most important the 3D CTF correction is, which is something what we expected, but it was always nice to have it confirmed also by numbers. And when we did it, we computed the, we ran the analysis with the new starting positions and with the same amount of data. We really ended up with improvement. We tried also phase flip to be fair, because originally I said that this data set was corrected with phase flip technique, and we tried phase flip. That was also better. The multiplication was slightly better. That's why I'm showing you this one. But already the phase flip was showing quite some improvement. And when we also used astigmatism correction, that we even improved it furthermore. And then the question was, because for the original data set, of course, there was no improvement after running few additional alignment. We tried to also run additional alignment here to see if it further improves, and it actually really did. And in the end, we ended up with the resolution of 3.4 in comparison to the original 3.9. So at this resolution level, there was quite a jump. And this was not visible only on the FSC curves. We could also see it on the structure. So we compared certain features that were clear that were usually problematic, and we see that some features are really nicely bit more shaped and a bit more carved, and we had nicer details like here and here, or here. This is also a bit more nicely shaped. So we actually not only have it on the curves, but we could also see that the structure improved in general. We are very happy about this. But we decided that it would be also interesting to take only 5 tomograms out of this 43 as a small representative subset and see if we have less data, if this difference between the 2D and 3D CTF actually gets more prominent, or if it gets less important. And also, one interesting question was if we actually need to do have a CTF corrected tomograms from the very early stages of subtomogram averaging, because similar to single particle, we never work with the full data set or with unbinned data set at the beginning. We always first downsample a lot. We do our alignment, and once we cannot improve more and we reach the Nyquist for the given sampling, we upsample and we go one step higher. And at these lower binnings or the lower at these lower downsamplings, people tend to think that the CTF doesn't play any role. So what is the point to actually bother at this stage? And maybe it's enough to actually go only to wait till the very end to have the 3D CTF or 2D CTF corrected tomograms. But we showed actually that this is not true. So we ran on this, we started from scratch. We ran these 5 tomograms with the 2D CTF approach fully. And we ended up having 4.5 angstrom structure. And then we took this positions and orientations found in this 2D CTF approach and just cut out the subtomograms from the 3D CTF corrected tomograms and use those positions and orientations to just average to see what, and that was already quite an improvement. It was like, I think 4.1. But if we really started with the proper 3D CTF from the very beginning, although it was not so apparent, we actually reached the resolution of 3.9. So we are able to get the same resolution as from the original 2D CTF corrected data set, but only with 10% of the data. And so this shows that, first of all, it pays off to really do the proper processing. And second of all, it also pays off to start as early as possible with the best possible data you can. And again, not to just show this on the curve. So the data set with the 5 tomograms, as I said, was having the same resolution as the all tomograms from with 2D CTF, but it was a bit more noisy. And some details here got a bit lost, but some of them actually got nice, like here. So we could see that all these features that were crucial for this 3.9 were also there. Some were even nicer, but some were, but the map was definitely a bit more noisy, and sometimes we also lost a bit. So, but still, it was very, for us, very important result to know that we actually could get to the same resolution and most importantly to the same structure using only 10% of the data when we really did the processing properly. And the price to pay for it, so to speak, of course, there is a bit more computational time necessary, depending on how your resources are handled in your institute. But if these numbers are for the data set from the 4 years back, and I think all these numbers are now way better with better hardware. But just to compare the IMOT, the CTF correction, because it's 2D strip based, it takes actually some time, while we do only normal CTF correction, so it's actually very fast. So depending on how many times you have to perform it, you spend more time here. But then the reconstruction itself is not so much more, and most importantly, it does not increase with the number of the correction. So if you have 33 tilt series instead of 1 or 45 instead of 1, the difference is not much more here in this reconstruction time. And all in all, when I compare the original reconstruction time for the original data set was 51 minutes per tomogram, while we have 2 hours, was not so bad given the improvement. Now this also can be parallelized. So what we now normally do is that we run all of these corrections at once on clusters, so that basically makes this 1 hour being rather 2 minutes, and the time-wise we are very comparable to IMOD right now. What is a bit worse is the temporary storage. So memory-wise, again, because we have it very efficiently implemented, it doesn't matter how many tilt series you have to correct. The RAM memory you use or the program needs is very, very low. It's even lower than IMOD actually. What is a bit higher and what is dependent on how many corrections you do is the temporary storage, because obviously one tilt series in this case has 2 gigabytes. So if you have 33, then you have 66 gigabytes more, and with each new tilt series you get more 2 gigabytes. You need more, but this is something you need for the reconstruction. as a storage. Once you have your tomogram, you can delete it, so it's also really temporary and not really, typically a bottleneck for us. And here I would like to spend a bit more on what we actually do, what is our typical tomographic workflow. So when we use novaCTF, so normally we start with the motion correction. That's for us happening already on the during the acquisition. We're using cryoEM. Then we do the CTF estimation. We typically use CTF find 4 or GCTF, depending on the data. Then we do dose filtering, which is very important to get rid of the damaging high frequencies. Then we do tilt series cleaning, where we really go through all tilt series and remove all the images that we think are suboptimal in terms of quality. Then we go to this classical e-tomo processing, and we establish mostly to establish the parameters for the alignment of the tilt series, but also to get the preliminary normal weighted back projection reconstruction of the tomograms to see if we actually like what we see, if we have the structure what we need there, and to maybe determine some Z shift and the thickness of the tomogram. And then we go for novaCTF, which means that we first, based on the CTF estimation, typically we decide how much we trust our CTF estimation and how fine we want to sample the reconstruction space. So we have this defocus step determined. Then we do the CTF correction. We do the tilt series alignment only after this, using the parameters established in step 5. If we have gold bits, we remove them. Then we do the reconstruction with the 3D CTF correction, and then this is on unbinned data, and then we also directly produce the binnings that we need. So we typically work with twice, 4 times, and 8 times downsample data for subtomogram averaging, and then we go for subtomogram averaging, and then we do always only on the 3D CTF corrected tomogram. So we never use the tomograms that we reconstruct in e-tomo to do visual checks. We never use for any computational processing. That we always go with the 3D CTF corrected ones. And before I wrap up, there are 2 more things I would like to mention, because I'm getting these questions a lot. First one is we offer, our novaCTF offers 2 type of corrections. One is phase flip, one is multiplication. Phase flip looks very similar to the data you get when you do 2D strip-based phase flip correction, or just no correction whatsoever, while multiplication looks really terrible, and people are often scared and are asking me what they are doing wrong. Nothing, as long sorry, nothing, as long as you can still see at least a bit of the removed beads and the structures, and you know that this is actually, for instance, here this is a bit of the cut off from alignment, that if it's there. These are not artifacts. This is just really when you boost the amplitude using multiplication in the correction, this is how it looks like. So even from this kind of data, we still got this 3.4 angstrom structure. So you don't have to be worried that something is wrong. And the other comment is there are now more and more packages offering the CTF correction on subtomograms and on subtomogram level, claiming that this is more precise because you can do this per particle CTF similar to single particle, so you can, use the precise Z height of each of the particle and make it a bit more precise in terms of correction. However, there are a few problems with that to consider. First of all is that the CTF estimation in tilt series is not so precise. The differences in 1 nanometer defoci will not give you that much. We tested it a few times and we never got anything better going below this 15 nanometer slab. So this is more or less the precision that you should aim for. So for really like a smaller differences, this per particle thing is not so crucial because the estimation is not so precise. And then, as I already mentioned before, typically it's not enough to use the Z height. So here again, this is the same Z height in the tomogram, but both voxels would be modulated with different defoci values based on the tilting. So claiming that you use Z height to make it more precise is actually not entirely correct, because you would have to also consider X. And that brings me to the last problem, is that at the moment you have your subtomogram already reconstructed, then each subtomogram is a value that is basically consisting of a sum of 40 different or as many different values as you have a field series, and it is actually representing modulation by 40 different defoci values. So using one defocus value to actually try to correct for it is not making it more precise, it's actually making it way less precise. That being stated, I'm not saying that this is not a working approach, it is. It's definitely better than no CTF correction, and it's better most likely also than the 2D strip-based approach. And it provides a decent approximation. It's just that mathematically speaking, it's not really a proper 3D CTF correction, and one should be aware of that and when one considers to use this approach. And with that, I would like to wrap up that, we showed, and by now it's clear, that using the 3D CTF correction and taking the thickness into account really provides better results than the 2D CTF approach. And especially for high resolution subtomogram averaging, it's crucial to actually take it into account. novaCTF is now going to be part also of Scipion, but it's even outside of Scipion, was implemented in a way that it should be very complementary to iMode. So you should be able to use your typical iMode or iTomo tomography pipeline and just switch to novaCTF at the very end or in the middle. And in the past 4 years, we use it normally now routinely for all the subtomogram averaging projects. I think that people from John Briggs also still stick to this one. Might change now with new Relion, but let's see. And I know that in the past 4 years, I got many requests for help, and in the end, many positive feedback from many laboratories that actually managed to improve the resolution while using novaCTF. So I hope it will still remain that way. And for me, one of the most important thing here, I think, is that we also show that when you spend some time on processing and when you don't try to cut the corners there, you actually can achieve a really nice results with not so much data. And I think that especially in times when not everyone has unlimited access to the good microscopes, it's very good to know that one can still squeeze out much more from the data if one takes its own time. And I also hope that I showed you on these nice spheres or disks that in any case, no matter what resolution you aim for, not even if you don't even have to aim for resolution necessary, I believe. It's basically any CTF correction is better than no correction. And it doesn't matter really what resolution you aim for, because in the end, it's also the fact that the structures are just distorted. And you do not want that. Even if you just want to analyze your tomograms and do not want to go for subtomogram averaging, it still pays off to have the structure as nice as possible. So doing CTF correction and compensating at least partially for some of these distortion always pays off. And with that, I would also like to mention that this is not a dead project. We haven't been updating it for a while, but right now, currently, there is someone working on support for a direct particle reconstruction. So if you already have your particles, and you have only few of them per tomogram, you might not want to reconstruct the whole tomogram, just directly the particles. It will be still the same implementation, only it will save you, I guess, some time and storage space. We also want to add the support for the x-axis still, that is currently not there, and most importantly, because we realized how much it can also improve the resolution, is the use of local alignments that is currently not supported, that will be also in the course of next month added. And finally, if any of you is interested in the software method development, I'm having 2 positions open, one for PhD and one for postdoc. So you can write me an email or check my website for more information and get in touch with me. And with that, I would like to thank all the people that worked on this. So my co-authors Florian Schur, William Van, and of course John Briggs. Back then, many people in John Briggs' labs, both at EMB and LMB for testing. Simon Matei, Dustin Morado, Julia Poikes, and Aaron Tan, mostly. David Mastronarde, so the author from iMod, that actually spent a lot of time explaining some things, how it works, and of course my current laboratory in Martin Beck's group at MPI, where I can still continue working on the things I like. And thank you for your attention.
Thank you, Beata. It was a really nice talk. And there are one question in the chat, and if any of you have any other question, please you can write or directly ask. James Krieger asked if we can do as well with 10% of the data 5 tomograms using this approach as full dataset, then do you think that means we can classify more finely or continuously?
Now I'm not sure if I get the question, but yes. So ideally, if you can get the same resolution with less data, then it means that if you have some conformational changes in your data, because that's the problem, right? For tomography, the classification is typically not working because there is not enough data to really create meaningful classes typically. So yes, the better data you have, the better. I mean, if you reach the same resolution with less, sorry, with the less particles, then of course you have higher chances to classify them better if there are some conformational changes at this resolution that you would like to pick up.
Okay, thank you. I have another question, Beata. So thank you for the talk. And if I understood it right, when you do the multiplication correction mode, it is an envelope correction, is that?
Well, not really. I think it's very simple. So we basically no, I do not remember how exactly this is implemented, but you know, we just multiply with itself. Basically, that's how it works. So I'm not sure if the envelope. I think the envelope one is still a bit more sophisticated than what we do.
Okay. Okay. Yeah. And what do you think about the envelope correction? That is something that is needed, or because at the moment you are only doing phase flip or this multiplication mode?
Yeah. So I don't know. The thing is, it's not so hard to add because so for novaCTF especially, it's well, actually, you don't have to use novaCTF for correction in the first place. So you can also test it yourself by using the envelope correction outside and just use this tilt series as an input for the reconstruction. So this might be the easiest way to check if there is some improvement. I personally don't think you will gain that much, because it depends also, you know, all these things are sensitive to the estimation. So it's always a bit, for instance, we often use phase flip only because it's less sensitive to the estimation error. So it also depends a bit on if you trust, if your data is good enough and you trust the estimation being precise enough, if it pays off to actually go for multiplication or for this envelope, I would say. It will be data dependent to test this.
Thank you.
Okay, I think there are people asking. Meanwhile, I would like to, well, James is already asked. James Krieger asked, can you explain more what you mean by multiplication, please?
Yes, that's basically you take the signal and you multiply it with itself. So the negative values become positive, and you also boost the amplitude. So you know, if you do phase flip, you just really invert only the contrast. So what was negative becomes positive in those waves or in those graphs. In the multiplication, you also kind of multiply with itself, so you push the amplitude more closer to the 1. But this is more sensitive, as I said, to the imprecisions in estimation. So closer to the 0 points, this can get a bit more messy. But mathematically speaking, this is just really a multiplication of the Fourier spectra.
Thank you, Beata. In this regard, my question was related with this, and I looking at the images, I have the feeling that like the multiplication changed the spectra, like a kind of whitening or something like that. So it's because of the boosting of the.
It's because of it. So it's making the things more even and less contrast.
By the inverse of the CTF or by the CTF?
This is the question. No, by the inverse, because the division would be very tricky close to the 0. So I think we really multiply with itself. But I don't want to now, because I was dealing with that already once, and I'm not 100% sure.
Yeah, because that would make it more like a comb rather than flat, no?
Yeah. Yeah.
Mm-hmm. That is typical in normal equation solving. So you multiply by the CTF, not by the inverse of the CTF.
Yeah. So we did what we did originally was, again, because we wanted to have the very as close comparison to IMOD as we could, because we wanted to compare it. So we took also the multiplication procedure from IMOD. It's just we removed the stripped base thing from there. So it was more or less it. Yeah.
Thank you, Beata. As an IM, ask for a thick sample, the data collected by an electron microscope is a projection of the sample. When a computer tries to slice it and assign different defocus values to each slice, how does a computer know where a signal comes from? Does it require image guys at different series of angle to retrieve this information?
So now I'm not sure if I understand the question correctly, but the thing is, yes. One of the problem that we have, or it's generally not solved, is, of course, you get this 2D image that is a representation of your 3D thing, and you do not know then when you estimate where the defocus was estimated. So if it was, center, typically we take it as a center of your density. So if you look at your tomogram, you have some distribution of your structures in it, and you assume that in somehow an average height of those, your defocus was estimated. So you place it basically back there. You can see when there is a carbon in your sample that comes into the image. You can see, for instance, that once you tilt, then the defocus estimation is actually really like drawing some nice curve, and you can clearly see that the estimation was not done where your structures are, but where the carbon is. So this was one of the things. And novaCTF has this additional defocus file parameter where you can say, okay, I know that this estimated value is shifted by 200 nanometers because it's at carbon and not in the middle of my densities. And you can fetch this information into the novaCTF to actually recompute the proper center of the estimation. So you can say, okay, so this was estimated at the carbon, but I know my densities are actually 200 nanometers lower, so shifted by this much. But generally, it is a problem because we always assume it's somehow middle of our densities, but we do not know that. And the question how much it influences it when you are off the center is something that is very hard to test because we do not know. I mean, you can test it on one data set, but it's more the question how to make sure that we got it right for the new data sets, right? So you like to be able to place it correctly. And what we typically do is we run our workflow once we have all our particles and our final structure. We often take the average Z height of those particles, if they cover somehow more or less our tomogram space, then we take them and we reconstruct again with novaCTF using this additional shift, saying, okay, now we have more precise center of our densities. Let's try to reconstruct again with this. And then we just recompute the average and see if it improves or not. Often it does a bit improve to make it like a bit more precise. So there is a possibility to do that. But other than that, it's generally an unsolved problem how to provide some general guidance where this defocus was actually estimated, especially in tilted cases.
Thank you, Beata. And finally, Jose Maria Carazo asked, so you are using the CTF in the forward image formation model, so the multiplication, I guess. In this way, do you have to deal with dividing by zero, by close to zero?
No, because as I said, we multiply with the CTF itself, so the multiplication is not a problem. The zero remains zero, and we hope to have enough coverage of this by having many tomograms from different defoci ranges, basically.
Yeah. Thank you. And I think there are no more questions. So just thank you again for this amazing talk.